So before you read this, before you watch this, I should say, I want you to read pages 784 to 787 in your book, just so that when I go over it, you've kind of seen it somewhere else before, which will allow me to go a little bit faster. So if you haven't done that, hit pause and read 4 pages and then come back. So what we're going to talk about here are direction cosines. And one of the ways we like to talk about vectors, beyond just its magnitude and the angle it might make with the positive x-axis, is what angle does it make with the positive x-axis, the positive y-axis, and the positive z-axis. And these 3 things are called the direction angles of that vector. And so alpha is the angle it makes with the positive x-axis, beta is the angle it makes with the positive y-axis, and gamma is the angle it makes with the positive z-axis. So since the x, y, and z axes are parallel to the standard unit vectors I, j, and k, let's say we know that v, the vector v, is components v1, v2, and v3. What's the component form for I? Well, the component form for I is 1, 0, 0. That makes sense. If I want to use the formula now for cos theta, I can use the dot product cosine formula to create a formula that will calculate me alpha. So alpha is really the angle between I and v, so cosine alpha would be I dot v over the magnitude of I times the magnitude of v. And so if I do that, I is 1, 0, 0, v is v1, v2, v3, the magnitude of I is 1, and the magnitude of v is the square root of v1 squared plus v2 squared plus v3 squared. And if I simplify this, I have 1 times v1 plus 0 plus 0, so cosine alpha is just v1 over the magnitude of v. And if you can kind of see, if instead of using I and v, I use j and v, everything on top is going to cancel except for v2. And if I use k and v, everything on top is going to cancel except for v3 because k is 0, 0, 1. So hopefully you can see what I'm trying to get at here. And basically you can use that simplifying process because I, j, and k have 2 components that are 0 to say that cosine alpha is going to be v1 over the magnitude of v. Cosine beta is going to be v2 over the magnitude of v. And cosine gamma is going to be v3 over the magnitude of v. And that's it. So if I want to find the direction angle for vector w for negative 2, 7, I can just use these shortcuts and say, well, cosine alpha, alpha being the angle between vector w and the x-axis, cosine alpha is going to be the first component over the magnitude, which is going to be 16 plus 4 plus 49, which is going to be 4 over root 69. And then cosine beta is going to be negative 2 over the square root of 69. And cosine gamma is going to be 7 over the square root of 69. And so if I actually want to calculate those angles, right now we can be in degrees. It's fine. We're not doing derivatives, so degrees are fine right now for Calc 3. And so if I do inverse cosine of 4 divided by the square root of 69, I am going to get alpha equals 61.213. So I'll just say approximately 61. Beta negative 2 over root 69, going to be negative 2 over root 69. So beta is 103.9, so I'll say 104. And then gamma 7 over root 69. And we get 32.57, so I'll say 33. And notice these don't add to 180 or anything like that. They don't need to. These are just three separate angles that are relatively independent of one another. Okay? All right, now we're going to talk about something a little awkward, and that's projections and vector components. So, long story short, if I have a vector u right here, and I say, okay, here's this vector u, and I have another vector that's been given to me, this vector v, there are some cases where I want to figure out, okay, I want to know two vectors that are perpendicular to one another, w1 and w2, that add up to u, okay, where one of them is in the direction of v. Also, things I might want to know about that is if I look at u and v, I might want to know, well, u is being pulled up here for like something like work. I'm pulling on a rope that's in this angle, but when I pull that rope, I have a box that's going to move in this direction. So how does this angle affect that direction? So that's what projections are all about. So let u and v be non-zero vectors. Let u be w1 plus a w2, where w1 is parallel to v and w2 is orthogonal to v. w1, this one down here, is called the projection of u onto v, or the vector component of u along v, and is denoted by w1 equals the projection of u onto v with this notation. Since w2 is really part of the sum that makes u, since u equals w1 plus w2, then w2 is u minus w1, and that's called the vector component of u orthogonal to v. So here's what it's going to look like if the angle is acute. Here's what it looks like if the angle is obtuse. And basically, we're just going to follow the rules right now, and you can think about what it means later as we look at some applications, okay? So if you want to get that projection, there is a formula for it. The projection of u onto v is u dot v over the magnitude of v squared times the vector v. And the reason this makes sense here is all of this turns into a scalar. U dot v is a dot product, that's a scalar. Magnitude of v squared, that's a scalar. So u dot v over the magnitude of v squared is a number times v, which makes this a vector in the same direction of v, a vector parallel to v. Okie doke. All right, so let's just use that formula to find the projection of u onto v and the vector component of u orthogonal to v. So here's u, here's v. Let's do the projection. So I have the projection of u onto v is going to be u dot v over the magnitude of v squared times vector v. So let's see, our dot product on top is going to be 12 minus 4 minus 27. And on the bottom, the square root and the square root cancel out. So I have 37 plus 81, which is 118, if I'm not mistaken, times 6, 1, negative 9. And let's see, 12 minus 4 is 8. 8 minus 27 is negative 19 over 118 times 6, 1, negative 9. That's the projection. If you want, you can distribute this, but you don't have to. That's the projection. So again, here's u, here's v. Your projection that we just created is this thing right here. That's that vector. Now I want this vector so that the two green ones add up to u. So the, where is it? So the projection of u onto v is given, and the vector component of u orthogonal to v is going to be what we call w2, and that's u minus w1, which is going to be 2, negative 4, 3, minus negative 19 over 118, 6, 1, negative 9. And this is kind of gross. Let's see here. I'm going to have 2 plus 19 divided by 118, because it's minus negative, times 6. So our first component is 2.966. Our second component is going to be negative 4 plus 19 divided by 118 times 1. Negative 3.839. And then our last component, which it's going to bother me here that these are all separate, but it's what I got to do. This last component is going to be 3. This is going to be minus a negative times a negative, so I'm going to do 3 minus 19 over 118 times 9, 1.551. If I could write with this, that would be helpful. 1.551. And there you go. That's just what it is, just using the formula. Now, why do we care? Well, one of the major reasons why we care is work. Work in physics is force times distance. Work is magnitude of the force times the distance traveled. Well, what if you're not pulling in the same direction that you're traveling? That means work is a projection. Because if I have, let's say, a wagon, all right, so here's a wagon, a nice little radio flyer wagon here. And I'm pulling the wagon, I'm pulling it at this angle right here. So whatever this theta is how I'm pulling the wagon. And let's say I pull my wagon 20 feet using a force of 10 pounds, okay? Well, what I really need for the force vector is I need this vector right here. That's the projection of the handle on the distance, okay? So work is really the magnitude of the projection times the distance, and what happens is this simplifies very nicely into F dot PQ. Okay? The reason it simplifies very nicely into F dot PQ is this projection equation right here ends up being F dot PQ over the magnitude of PQ squared times PQ. We're taking the magnitude of that and we're multiplying it by the magnitude of PQ itself. So here's the projections magnitude. There's PQ. I'm using this formula right here. And if you really take this apart, I have F dot PQ over the magnitude of PQ times PQ over the magnitude of PQ. And I'm taking the magnitude of that. Well, the magnitude of this whole thing can ignore that because this is a unit vector. A vector divided by itself, that's a unit vector, right? And then when I have this guy, now that I've eliminated really the vector altogether, I'm sorry, I haven't eliminated the vector. Since I've made a unit vector and I'm multiplying it by this other coefficient, the magnitude of a unit vector times this coefficient is just the coefficient itself times the magnitude of PQ. Well, wait a minute, there's one there and one there. I just end up with F dot PQ. If you didn't follow all that, it's okay. You really just need to know that work is F dot PQ, where F is your force vector. So let's say I want to slide a door closed using an angle of 60 degrees, and I have a 50-pound force. Well, then my force vector is 50 cosine negative 60, because technically I'm pulling underneath here, and then 50 sine negative 60. That's my force vector. And then my PQ vector, remember my PQ vector right there? My PQ vector is just the distance I travel, which is to the right. How far? 12 feet. So if I go 12 feet to the right, that's 12, 0. And so if I do F dot PQ, I get 50 cosine 60, which is 50 times 1/2, and then 50 sine 60, which is 50 times negative root 3 over 2, and I'm dotting that with 12, 0, so I get 25 times 12, which is 300. That's the work done. What if you were pulling 12 feet at an angle of 75 degrees? What about 20 degrees? You do the same exact same thing, except change that to 75 and 20. Okay? So hopefully all of that made sense, and you can work on the problem set. I need to end with a joke here, so my joke today is, what kind of bed does a mermaid sleep in? A water bed. It's not a good one, but it's a cute one. All right, enjoy the rest of your day, evening, morning, whatever time it happens to be.